So thanks all for coming in great numbers. Some time ago, Françoise asked me to give a general sort of overview of what we're doing related to DAS and fiber optic sensing within Géoazur. So what I'm going to do in this, well, I guess relatively informal seminar is I'm going to give you a short overview of fiber and fiber optic sensing. And also some of the technologies that are associated with that. Not everything uses the same kind of technology. And then I'm just going to race through a whole number of examples in geophysics, focusing on the work that we're doing at Géoazur, but also with a few examples from elsewhere. Feel free to interrupt me if you have questions. I think there should be enough time for discussion, so I can go back to some of these examples and talk more about it, or we can ask some of the people here in the room about it. I also have to manage the Zoom at the same time, so I'm going back and forth between the Zoom to let people in and the presentation. Okay, so beginning with some history. I guess so the whole reason why fiber optic sensing and telecommunication works is because we have this phenomenon of total internal reflectance. And this phenomenon was initially attributed to Johannes Kepler, even though already before him there were some mentions of this idea, and also the law of total internal reflection that he came up with was wrong. Later it was corrected. But anyway, so the idea that you can manipulate light, I guess, started somewhere around there. And then the first actual waveguide was created by Corandon and Babinet in 1840 in Paris. And it looked like that. It's a stick. So here is basically a bucket of water, and you poke a hole in it. And so there's this stream of water coming out. And then if you inject a light into this bucket, then it will sort of stay within this stream of water. So it will sort of bounce around and it will follow the stream. And so this is, I guess, the first example of a proper waveguide for the light. Of course, this is just a gimmick, but at some point people started to use this to transmit information. And I think the first example of transmitting data was made about 100 years later by a Dutch guy called Bram van Heel. And apparently he is famous for saying that, well, I'll start in Dutch, het licht komt altijd van links behalve als het van rechts komt, which translates into the light always comes from the left unless it comes from the right. So he had this Johan Cruyff style of philosophy, I guess. And so this was the first transmission of images through optical fiber. Then at that point, fiber optics didn't really exist yet. The term fiber optics was actually coined by this man over here, Narinder Singh Kapeni, Indian-American scientist who wrote an article in this popular science magazine, Scientific American, where he first made a mention of fiber optics. And I think this is really the start of the modern era of fiber optics. Because soon after, people started to transmit actual data through optical fibers. Also in the coffee room, we've been discussing the possibility of putting fiber on Mars. Well, NASA did it first on the moon, not to record moonquakes, but to actually transmit data within a camera. So this is Neil Armstrong's camera that actually contains some fiber to transmit data within the camera. But at this point, fiber optics and transmitting data through fiber optics was limited to relatively short distances. That was because fiber still had relatively high attenuation, so your signal degrades relatively quickly over longer distances. And it was really this invention or this manufacturing technique developed by Kao and Hockham that brought fiber attenuation to something less than 20 decibels per kilometer, which made it competitive with copper. And this invention actually won the Nobel Prize in 2009. So it is really thanks to these guys that we are able to transmit data over longer distances in fiber. And so around the early 1970s, they brought down even further to about 4 decibels per kilometer, meaning that you can really cover large distances with fiber. Another issue that we were facing, well, let me first mention that the first example of really like having a data transmission outside of a lab, sort of out in the real world, was demonstrated by this little experiment that was done in Turin, where they had a deployment outside and where they transmitted data over this, I guess this is maybe a few hundred meters of cable. So this was sort of the first urban or metropolitan cable loop that was being used. But if you want to transmit data over large distances, you of course also need very long cables. And well, up to the 80s, fiber was relatively slow to manufacture. So creating these fiber strands, they could do it at a rate of about 2 meters per second. And if you need hundreds and hundreds of kilometers of fiber, that is really too slow. But Thomas Mensa found a way to increase this rate up to 50 meters per second. And so thanks to this increase in speed, it now became also cheaper to make fiber than it was to make copper, because the material costs are lower, and now also the rate of production is sufficiently high that with a single machine you can manufacture enough fiber to make it competitive. Okay, so from the 80s onward, optical fiber is both cheaper than copper and also has less attenuation. And so this is perfect for large-scale telecommunication. Another reason why you want to use fiber instead of copper is because it is really, really fast. How fast really depends on a number of factors, including the distance over which you're communicating and number of channels, etc., and also depends on how you measure it exactly. But the current world record for the fastest or the largest aggregate bandwidth is currently set at over 10 petabits per second. This number may not mean much to you, but this is fast enough to transmit all the seismic data stored at IRIS in less than 1 second. So IRIS has accumulated about 1,000 terabytes of data. The entire internet is estimated to be about 25 million petabytes in size. Don't ask me how they measure this. And to transmit the entire internet to your computer would take about 7 months at this rate, which is, well, it takes a while, but then you have at least all the internet on your hard disk. Of course, there are lots of other limiting factors here. This is a particular experimental setup that eliminates as many bottlenecks as possible. So this is not going to be feasible in the near future for your whole network. But still, this kind of shows that theoretically, there doesn't seem to be an upper limit to how much you can transfer through fiber. And for these reasons, let me and so for these reasons, optical fiber networks are vast and still growing around the world. This graph here on the right indicates the number of broadband connections or the percentage of broadband connections that are using fiber. I just highlighted France in here. So the blue bar is the percentage in 2020, and then it goes up to 2022. So in the span of 2 years, France has expanded its fiber optic network by over 20%, which is, on this list is pretty significant, because only Costa Rica and Chile have had a larger, faster expansion of their fiber network than France. So now it's already 1 year later, so hopefully it will be far enough to the left so that I can also get internet, fiber internet at my home. But aside from just telecommunication, there are lots of other things that you can do with fiber. And so now I'm just going to give you a few examples. Of course, many of you here will be familiar with distributed fiber optic sensing, which is this great tool for geophysics. But there are some other things that you can do with fiber that are not distributed, and still I found it interesting just to mention them. For instance, you can use fiber as a gyroscope. If you have basically an optical loop like this, where your photons are being sent, in this sort of around this loop in this configuration, then you have this kind of interference pattern that you create where your photons are sort of meeting each other at the detector. And if your system is at rest, then, well, you have a particular interference pattern. But if this system starts to rotate, then the interference pattern changes. And so you can infer what is the rate of rotation of your loop based on the interference pattern. And so you can then create these sort of 3-component gyroscope by just creating these fiber loops. And this is actually being used in the Boeing 767. So they use this kind of technique for navigating airplanes. Something else that would be of interest is, for instance, measuring humidity or hydrogen content. Because if you take a fiber and you just cut it, and then you coat the end with a bit of palladium, then the hydrogen atoms will interact with the palladium, and then it will change the reflectance at the end of the fiber. So if you send in a pulse of light, it hits the end and it will cause a reflection going back. And the amount of reflection changes depending on how much hydrogen has been absorbed by this coating at the end. And so you can use this in an industrial setting, for instance, to measure either humidity or hydrogen in the atmosphere. And the last example I just want to point out is that you can use this for acoustic communication in MRI rooms. So MRI is this massive magnet that you put your patient in the magnet and then you probe it. And because it's such a huge magnet, you cannot have any metal components in the room, because that will just get attracted to the magnet and potentially killing your patient. So all the components that you need, that you have in this room, cannot be made of metal. So having a microphone in the room is a bit tricky to make. But apparently they managed to make it out of fiber. So don't ask me how they did it, because that is all confidential, I suppose. But they make these microphones with no metal components out of fiber, so that there can be communication from there to other rooms that are shielded. Okay, well, these were just a few examples of fiber, of use of fiber that are not based on scattering, which we're using for distributed acoustics, distributed fiber optic sensing. And when it comes to distributed sensing, there are 3 types of scattering that we can use for different applications. The one that many of you will be most familiar with is the Rayleigh scattering, on which distributed acoustic sensing is based. This is also the same type of scattering that happens in the atmosphere. That's why the sky is blue, because blue gets scattered more easily than other wavelengths of light. But there are other types of scattering called Brillouin and Raman scattering that are inelastic scattering types. And I'll just go through them one by one. So first, Rayleigh scattering. This comes from interaction of your photons with with tiny manufacturing defects, so tiny density variations in the glass that are much smaller than the wavelength of light. And so whenever a photon meets one of these defects, it causes scattering, elastic scattering of the photon. So it will be sent in a random direction, but it will keep the same wavelength. So here's an example of that. So here's a laser that shines into a plastic cylinder. And well, you can see this light bouncing around. This is a very nice multi-mode waveguide. But the reason that you can actually see the light bouncing around is because there are photons coming towards you, right? They're coming towards the camera or towards your eye. And so this is the result of scattering. That there are these tiny defects that cause the light to be scattered in random directions. Some of it will be sent towards you. Other scattered photons will be sent back in the same way they came. So if you have a light source here and you send in a pulse of light, and then you put a photon detector or a similar instrument at the same location, then you will measure essentially an optical echo coming back. And the phase of the light that comes back is proportional to the length of the path that it traveled. So if there is any changes in the length of the path, so if your fiber is stretching or shrinking, then you'll measure a change in the phase. And so you can infer exactly by how much your cable is stretching and shrinking. And this is the basis for distributed acoustic sensing. We really measure how much longer does the fiber get over the entire length. We can turn this into a distributed measurement by basically looking at the timing at which the light comes in. So if you send in a pulse of light, you will continuously record light being scattered coming back. And that two-way travel time, you convert into distance using the speed of light in glass. So you know exactly at what point in the cable you have your scattering and change in the phase. But there are these two other types of scattering. The first one, it's called the Raman scattering. This is an inelastic interaction between a photon and the molecule. So here we have some molecule of glass that is vibrating. A photon hits this molecule, and then it can emit a new photon, which has a wavelength either smaller than the original wavelength, so it has absorbed energy from the molecule, or it emits a photon with a longer wavelength, which then has given up or transmitted energy from the photon to the molecule. And these are called the Stokes and anti-Stokes components. So if you measure the light coming back and you look at the spectrum, you get two peaks. So one is the Stokes and the other is the anti-Stokes component. And so the transfer of energy from a molecule to the photon, so the anti-Stokes component, is proportional to the temperature at which the molecule is sitting. The other way around, transmitting energy from the photon to the molecule is less temperature sensitive. And so if your temperature is changing, then the relative peaks of the Stokes and anti-Stokes components are changing. So if you just take the ratio of the peaks of your Stokes and anti-Stokes Raman peaks, then that will be a measure of the temperature of your molecule. And so in this way, we can measure the absolute temperature of the glass by just looking at the ratio of these spectra. Something similar, a similar approach is taken with P1 sensing. So for Raman, we're looking at the vibrations of individual molecules. But because glass is essentially quasi-lattice, you also have vibrations of the lattice itself. So you have these acoustic waves essentially traveling through the glass, causing the glass to resonate. And if you then send in a light wave with a given wavelength, it has some probability of interacting with those acoustic waves that are traveling through the lattice. And this interaction between the optical wave and the acoustic wave causes Brillouin scattering. And so what you can then do is you measure the spectrum of light coming back in the Raman, in the Brillouin range. This gives you basically a symmetric peak for the Stokes and anti-Stokes components. And the position and also the intensity of this peak are controlled by the temperature of the lattice, but also the strain in the lattice. So with this technique, we can both measure strain and temperature, or at least temperature changes, independently from each other, because we measure both the peak and the frequency of the intensity and the frequency of the Brillouin spectrum. So at least in theory, we can separate them independently. In practice, it doesn't work so well. But anyway, there's still some progress to be made there. Also, these measurements are long-term stable. They don't depend on some baseline that may change over time. So if you make a measurement with either Raman or Brillouin, and then you were to unplug your instrument and come back a year later and you plug it back in, if nothing has changed, then you measure exactly the same thing again. So unlike Rayleigh scattering, this is a long-term stable measurement.
Martin, what's the maximum distance for
about 20 kilometers, I think. It's standard technology. Okay, so based on these three types of scattering, we have different types of distributed fiber-optic sensing. So distributed acoustic sensing, or DAS, is one that is very popular in geophysics. The underlying technology is what's called phase optical time domain reflectrometry. There is a frequency domain brother of that, which is called optical frequency domain reflectrometry. With DAS, you get excellent range and time sampling resolution, relatively poor spatial resolution, but good enough for geophysics. But with OFDR, we can achieve a spatial resolution of the order of a millimeter or less at the cost of a much lower temporal resolution, usually at around 1 Hertz. But then based on the other two types of scattering, we can do distributed temperature sensing, and we can do this what's called distributed strain and temperature sensing, so measuring strain and temperature at the same time. Okay, so what I'm going to do now is I'm just going to race through a whole range of examples of how we can use mostly distributed acoustic sensing in geophysics. But if I'm going too fast, or if you have a question, feel free to stop me and we can discuss more. Okay, so distributed acoustic sensing really took off thanks to the oil industry because fiber optic cables, they're very robust, and these type of measurements are not degraded by high temperatures, unlike most sort of standard sensors that as the temperature increases, you have worse and worse precision or measurement capabilities. So using fiber optics inside boreholes, especially deep boreholes, is really beneficial. Also, your instruments, so all your electronics and all your computations are done in this nice air-conditioned room, somewhere in a nice office or something like that. So you don't have to actually put your instruments exactly where you want to make your measurement. Instead, you put a fiber down there and your actual instrument is at the other end of the fiber. So you don't have to protect it from harsh conditions. And so with fiber, you can get all sorts of interesting measurements like absolute temperature, but also, so this is nice for monitoring fluid injections because fluid is colder than the surroundings. And so you can monitor exactly where is your plume of fluid. You can measure strain in the borehole to estimate stresses or if the borehole is being sheared or not. And of course, you can measure vibrations, so things like microseismicity can be recorded inside boreholes very nicely with fiber. And with distributed acoustic sensing, we have this sort of array of seismometers, one component seismometers, that you can very easily deploy. So this gives you very nice and very dense spatial coverage for active seismics and tomography. But you don't necessarily have to put your fiber in a borehole. You can also basically dig a trench and put your fiber in there. So here's an example from the Brady Hot Springs geothermal field in Nevada, in USA. This is a map view. This is 2 by 2 kilometers of the site where they deployed a fiber optic cable. This is the red line, zigzag over there. And then they supplemented that with a pretty dense array of about 250 nodal seismometers. Those are all the black dots. And this project sort of started for monitoring microseismicity and shallow subsurface imaging, etc., to monitor this geothermal field. But we can also use this data for testing new analysis techniques, like array-based techniques such as beamforming. So this is an example from a few years ago that I worked on with Pablo, where we compared if we do beamforming of an earthquake with the fiber optic cable, can we get the same performance as with the seismometers? Initially, the answer was no, but we managed to make it work. And so then we get kind of the same performance with both types of arrays. Another example of an onshore deployment that Géoazur was heavily involved in was the deployment around the Thai earthquake from a few years ago. So around Montélimar, we had this earthquake, and very quickly, I think it was Diane and Anne that deployed a lot of temporary receivers, and Anthony managed to plug in an instrument in local telecom cable that is indicated here in black. And so we were able to record, for instance, a large aftershock from this event. So this is what seismic data looks like in DAS. On the horizontal axis, we have time. Vertical axis is distance along the cable. So you can kind of see the whole wave field. And we can see that the earthquake sort of hits the cable first over here and then propagates to the extremities along the cable. And what is very nice about this example is that here we use an existing telecom cable, which we call dark fiber. Dark meaning that the fiber that we're sensing is not being lit or not being used for standard internet and telecommunication. And especially on land, there is a lot of fiber that has been deployed for telecom. And whenever they deploy a cable, there is a lot of redundancy in terms of the number of fibers that they put in the cable. So you can easily find a cable that has like 100 fibers in them, half of which are not being used because of the massive redundancy that they put in. Which means that, well, there are some fibers available that we could potentially tap into to do research like this.
Martijn,
Yes.
in this time section, is the first arrival a P wave and the second one an S wave?
Yes. The move out looks a bit similar, but the move out is, this is for P, this is for S. So this advantage of having many fibers in a cable doesn't necessarily apply to offshore environments, but still you can find cables that are not being used, that are being decommissioned, or where there is still extra fiber available. So this is an example from Toulon. This is Anthony's playground, if you like. He goes there regularly to do all sorts of experiments. So Toulon is over here, and then there's this cable that goes to a depth of about 2.5 kilometers to a decommissioned neutrino detector. And yeah, we have access to this cable to do all sorts of measurement campaigns. This is relatively cheap because Anthony just drives there and plugs in the instrument and that's it. So you don't have to pay for a ship, crew, instruments, pick it up, etc., which is extremely expensive. I guess Jan can tell us more about that. So we can now also monitor these offshore environments very easily with distributed acoustic sensing. So here's just one example of what you can do with it. So Gauthier won the student award on this paper, where he looks at the generation of microseismic noise. So using beamforming or back projection, you could sort of image which parts of along the coastline were responsible for generating microseismic noise, and he found that this changes over time depending on the direction of the winds and the currents. And now I'm actually currently employed by the ERC of Jan. It's called the ABYSS, which is a very large-scale campaign that's currently ongoing in Chile. Just to give you an idea of how big this campaign is, we right now have 3 interrogators. We have one sitting in over here. So this is Chile sort of superimposed on Europe, so you can see how long it really is. So this is Concon, and then we have 2 interrogators in La Serena. So we're sort of sensing this part of the fiber network in Chile, which is still only a small part of the entire length of it, but it's already a significant distance. It's kind of distance from here to Paris almost, in terms of the distance that we're sensing. And this the objective of this project are really to do subduction zone monitoring. So we're cataloging seismicity, we're looking at all sorts of seismic phenomena. The goal is to do precursory detection, either in terms of foreshocks or changes in the seismic velocities. And the ultimate goal is to develop an earthquake early warning system that is based on fiber, because all these cables are offshore, they're much closer to the trench, and they're closer to the action is happening. And so this can give you something like 10 or 20 seconds of lead time if you were to able to send an alert based on data coming from the cables. Of course, when you put your cables in the ocean, you will record more than just the standard seismicity. You also record lots of sort of ocean ambient noise or sounds, so ocean acoustics. At least we pretend that we measure the acoustics. We don't really, but still it's coming from the water column. So things that generate sound in the ocean are boats and whales and possibly fish, but also explosions and T-waves and things like that. And all these kind of things will also be recorded by these submarine cables. And this provides a very nice interface, I think, with other disciplines like oceanography, marine biology, acoustic engineering, all these kind of sort of related disciplines that can now integrate and collaborate with geophysics. So here's an example of a whale that has been recorded. So this is distance and time, and you can see very nicely sort of the move out of the acoustic wave that is sent by this whale. Something that's unnecessary. Yeah. Okay. Sorry, there was someone speaking, I think. Something somewhat related, but not necessarily acoustic or seismics, is that we can also record ocean currents in different ways. The first one makes use of the fact that we can't really control the deployment of cables offshore. You kind of, with your boat, you just sort of toss your cable in the water, and then eventually it will sink and then hits the bottom of the sea, but you don't really know what's down there. And very often we get into a situation like these, that your cable is sort of stuck on a chair or rocks, and so it is not touching the sea floor. So it doesn't record seismic energy anymore because it's sort of hanging in the water column. It is suspended. And just like if you span like a line, like a clothesline to dry your clothes outside, and it is windy and the wind blows past this string, then the string starts to vibrate in the wind and starts to whistle. And that's exactly what happens also when the water passes over a suspended cable. It causes the vibration of this cable, and the frequency of vibration is controlled by the rate at which water flows over it. And so if we look at the data and identify these suspended vibrating segments, we can actually use that to estimate the speed of the currents on the ocean floor. Using a completely different sort of approach. So this was the part of the PhD thesis of Daniel, and I think he's actually in the Zoom. But a completely different approach was taken by Julian, who looked at the very long period signals that are recorded with DAS. DAS is both sensitive to strain and to temperature at the same time, but strain coming from, for instance, earthquakes, relatively have a short period. If you look at the long period, then most of your signal comes from thermal changes. And so he used that to also monitor temperature changes over long time periods, which are associated with ocean currents and internal sort of circulation of water. An entirely different phase of water is ice. So this is not something that we've been doing at Géoazur, but Gosia has recently joined us. And so she was involved in these experiments on glaciers, where they deployed a cable on a glacier. And the very nice thing is that during the day, when the snow and ice melts a little bit, at night it freezes, and then it sort of binds the cable to the medium, so you have got very good coupling. And then you can use that to monitor things like rockfalls and like little acoustics and seismics coming from the base of the ice sheet and the glacier. And fiber is very easy to deploy, at least relatively speaking, because when you dig a trench, you put it in there, you cover it up, and that's all you need to do. And because fiber is so robust and also relatively cheap, of the order of about €1 per meter, you can deploy it in areas that are perhaps a little bit risky to put your instrumentation otherwise. So for instance, for landslides, here, this is one example that I found where they actually put it in a borehole, but you can imagine digging sort of a trench and putting your fiber on the landslide itself to monitor things like creep and maybe precursory activity like acoustic emissions coming from the landslide. From the studies that I've seen, most of them actually don't use distributed acoustic sensing for this because there's not much acoustics coming from the landslide, perhaps. Most of them actually rely on distributed strain sensing, so Brillouin-based sensing, to measure the slow, long period strain associated with creep of the landslide. But you can also imagine doing something like distributed temperature measurement, distributed temperature sensing, to estimate what is the rate of fluid flow if you have like a sort of a fluid conduit inside your sediments. And then the last kind of topic that still relates to geophysics, in my opinion, is urban monitoring, which is something that I've been doing for my previous postdoc. The reason that we can do this is because telecom cables are very often deployed alongside roads. It's very convenient to just deploy it alongside something that is already there. And so if you look at the data, then the first thing you see are cars. Whenever a car drives over the road, it generates all these vibrations that you can pick up with distributed acoustic sensing. But also simply the weight of the car that presses down on the road causes this stretching of the cable. And this is a very nice type of signal that is well understood. It is easy to analyze. So here on the left is one example. So this diagonal line here is a car. that is driving over the road. This is in a relatively long period band. If you look at higher frequencies, then it gets all a bit messy because of the surface waves that it generates. And but analyzing these type of signals can give you a very high resolution view on where the car is, how fast it is going, how big the car is. There's another paper that we recently got out where we actually counted the number of wheels on the vehicle, because there were these buses driving with, like, 6 pairs of wheels, and you could actually see individual wheels. And so Danielle, who he gave up his academic career to now become the CEO of a startup company to use DAS for traffic monitoring. And the final example is also something that is hot off the press, or still in the press. Diego recently submitted a paper describing an experiment that we did a few years ago on a bridge. So this is a bridge going over the A8 highway, connecting Antibes to Super Antibes. And so we had the fiber deployed on the deck of the bridge, and Diego was able to then extract these resonant modes of the bridge. And he found that there was actually a difference between summer and winter, because in summer the heat causes the bridge deck to expand, causing it to sort of lock up, jam inside the abutments, and so it's no longer able to move in the way that it does in winter. And so, yeah, so this is sort of the end of all the examples that I wanted to show, but there are still a few interesting things that we can look out for in the future. The first is that, so currently the range of DAS is limited to about 100 kilometers, or maybe 200 if you're really pushing it. But with some prototype technology, this group has been able to do DAS over a distance of more than 1,000 kilometers. So now we're really getting into this range where we can use this type of sensing for regions that are way farther offshore, like, say, mid-oceanic ridges and things like that. Also, I just briefly mentioned that offshore it is more difficult to get access to dark fiber, simply because they're using 100% of their capacity. So all of these cables are being used actively for internet communication. And that means there is nothing available for us to use, because, well, they would be losing money. But there are various companies that are working on technologies to do active sensing on fibers that are actively being used for telecommunication. So that means that a company no longer has to give up some revenue to let us make our measurements. Instead, they can just do their business as usual, and we can just piggyback on their fiber infrastructure to make our measurements. And the group in Spain is also working on developing an interrogator that is able to achieve a resolution that is much, much smaller than what we can typically achieve with distributed acoustic sensing. Normally, the lowest resolution you can get is about 1 meter. So you can make a measurement every meter along your cable. But they've been able to achieve resolutions that are less than 1 centimeter, which starts to make it interesting for instance, lab applications, that we can do lab experiments where we use fiber to record acoustic emissions or strain and things like that. And something that we just discussed over coffee with Jean-Mathieu was that there are also different types of sensing that you can use. For instance, this is called state of polarization, or SOP sensing, which measures not scattering, but it measures the light that actually comes out at the other end. So you send in a pulse of light, you put a detector on the other end of the cable, and you measure the polarization of the light that comes out. And if somewhere along the cable you have a perturbation, like an earthquake, then the polarization state changes over time. And so you can essentially record a waveform of the earthquake that occurred along this cable. And it doesn't give you any spatial resolution, because you have a single measurement for your entire cable, but you can do this over, say, 10,000 kilometers. So you can monitor a 10,000 kilometer long cable and get a sense for whether a strong earthquake is happening somewhere along that cable with this kind of technology. Andreas Wichner and his group have also been working on doing this using sort of the National Time Synchronization Network, which uses technology to counteract phase noise, which exactly gives you a similar result as with state of polarization sensing. So these are technologies that are still in the pipeline, but probably in the coming 5 years or so, we'll be able to make use of this in designing our campaigns and experiments. Okay, so that's all I wanted to show. Thank you very much.